Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Firan Aswad. I'm from Technique Industry batch 38 international class, and here I want to explain about operational research branch and bound material. Branch and bound is in the integer programming. The learning objective is understand the problem and solution integer variables, understand the method branch and bound. Integer programming is divided by 4, and the concept, solving method, linear to binary, and application. And then from the solving method we have a cutting plan and branch and bound. From the branch and bound we have integer programming, branching rules, and binary. From the cutting plan we have pure and mixed. Here the discussion is only intended for the integer linear programming problems. This is the type integer linear programming, pure integer linear programming, or pure integer linear programming MILP, integer linear programming mix, or mixed integer linear programming. Pure integer linear programming is PILP, and then binary integer linear programming is binary integer linear programming, or BILP. And this is the same from the previous slides. Okay, branch and bound method. Branch and bound algorithm. First, the method most widely used in practice to solve integer programming problems, either pure or mixed. Use mostly commercial software and basically an efficient enumeration procedure. To example, all feasible solutions are possible. The branch and bound method is like when in the production company, like when you want to make a car, and you need to find the optimal solution to make a car, and you can't just have a decimal solution, right? You need to have the best solution, like you can just have a 1.5 solution, and one car with another one just have half of it. You need to find the integers number from that solution. BB algorithm for ALP, PILP, and MILP. BB algorithm. Suppose given a programming problem's integers as follows: maximize z equals to cx, and the constraint is ax equal to b. X is more than 0, and x is more than equal with 0, and then xg, integer for g, element 1, where I is the set of variable integers. The first step is to solve the problem by ignoring the EILP as LP integer divided or bounding. Suppose a problem LP expressed as LP1, which has the optimum value of the objective function z1. LP1 maximize z equal cx with constraint ax equal to b. X is more than equal with 0. Assume that the optimal solution of the LP1 constrains several integer variables that have a fractional value. Therefore, the optimal solution for ILP integer not been obtained and becomes the upper limit or upper bound of the maximum value of z for ILP. The next step is partition the feasible region of the LP1 with branching one integer variable whose value fraction. Suppose that xg variable have to be combined with a fractional value dg or bg in LP1. Suppose the created to new linear programming problem, the LP2 and LP3 by entering each new constraint. xg is less than equal with b, and then xg is more than equal b, but there is a plus 1 for the next xg more than equal with. The same here for the LP2 and LP3, but because we use more than in the LP3, we must to remember that we give plus 1 for the number that we choose for the beta. This is the example about the LP1 fractional solution or Z1, and then we choose the number xj. The number of LP2 should be less than equal beta, but and then the number for LP3, this is not LP3, should be LP3, more than bg plus 1. The right one is must be LP2, and then it should be xg more than equal beta plus 1, not less than. Solve or bonding LP2 and LP3, and then assume solution LP2 and LP3 is still a fraction. You still need to calculate it, but if you find the number is stop and the number is already integer, you can stop and finish your work. The next step is to choose the node LP problem. Having been to branch LP problem further, the next step is choose a variable integer with a fractional value that will be branched to form the new LP problem or the process of branching. Solve the problem of the new LP or the bonding. If the integer solution obtained from an LP problem when its value z becomes the lower limit or lower bound of the maximum value of z for ILP, the same solution is we should do in the fractional solution in the LP5. If we don't find the integer solution in the LP5, we should calculate it again the same way from the first one, and then we will find the LP6 is a fractional solution and LP7 is also a fractional solution. The essence of the algorithm or baby bonding is branching and application of algorithm BB. The example is like maximize z is equal to 2x1 plus 3x2 with this constraint 5x1 plus 7x2 less than equal 35, and then 4x1 plus 9x2 less than equal 36. x1 and x2 is more than equal 0 and integer number. Here is our z 14x divided by 17, and then we choose to give the LP2 and LP3 is the number 2 and 3. Because we have the x1 is 3 and the x2 is 2, we should find the for the x2 is the lowest number for the LP2, and the lowest number between 2 and 6 divided by 17 is 2 in the integer number, and the higher number from between 2 no the higher number from 2 6 divided by 17. If we want to get it an integer number, we should have the upper number, and it's a 3. So we give in the LP3 is x2 is more than equal 3, and then in LP2 is x2 is lower less than equal 2, and then we calculate it again. The x2 in the LP2 is 2, and then in the LP3 we have the x2 is 3. And then we find the z, and then x1 of the LP2, and then LP3 is not an integer, so we will try to find it again. In the LP5 and LP4 it's the same thing, that we choose x1, and here is the x1 for 4 and 1 divided by 5, but because the lowest number is 4, should be in LP4, and then the higher number is 5, should be in LP5. And then here we are, we find the integer number in x1 and x2, and the z is also integer number in. So after we choose this LP4, we fathom, because the z number is, and the lower bound is less than 1, and all of the coefficient is integer, and this is our solution.